We will use the quotient rule when we have the quotient of two functions. So we're looking at division. We have function u divided by function v, or let's say function f of x divided by function g of x. So you will not do the derivative divided by the derivative. The only time we actually do a derivative over a derivative in this class is when we're doing L'Hopital's rule, and that's to evaluate limits, but not to take a derivative. So the way the quotient rule works, it'll be the bottom function, the denominator, times the derivative of the numerator. Then you'll subtract the numerator times the derivative of the bottom, the denominator, and it'll all be over the denominator squared. So that sounds very complicated, but it's the bottom, v, times the derivative of the top, u prime, minus the top, u, times derivative of the bottom, v prime, all over the bottom squared. If you see it with f of x and g of x, it's the bottom, g of x, times the derivative of the top, f prime of x, minus the top, f of x, times the derivative of the bottom, g prime of x, all over g of x squared. Now, one day I had really bad handwriting in class, and one of the kids said it looks like bat tab. So we always remember it as bat tab. The bat was really bottom, and then I had a derivative of the top. And it wasn't written exactly like this, but this was the idea. Minus the top times the derivative of the bottom, and you can see how it might kind of look like bat tab over the bottom squared. So bat tab over b squared. So for our first f of x here, we have 3 cosine x over divided by x squared plus 2x. So these are pretty easy to spot. It's not like product rule where sometimes you don't notice that you're multiplying two functions. You're definitely dividing two functions. So f prime of x will equal the bottom, x squared plus 2x, times the derivative of the top. That is a negative 3 sine x, minus the top, 3 cosine x, times the derivative of the bottom, and that is 2x plus 2, all over the bottom squared, x squared plus 2x squared. Now my advice to you is leave the denominator alone, because when we're actually working with these derivatives, generally we're setting them equal to 0, solving and doing things like that. It's fine the way it is. If I actually expand it, I'll probably end up trying to factor it again. And I could factor an x out here, but really just leave the denominator alone and simplify the numerator only. So I will say f prime of x equals, and I'm going to distribute the negative 3 sine x. So that is a negative 3 x squared sine x minus 6x sine x. Then I'll distribute the negative 3 cosine x, so negative 6x cosine x minus 6 cosine x. And maybe you'll see something else that cancels out, maybe you won't. There are things I could factor out. I could factor out a 3, and I'm not going to, because really the point is just can you do the quotient rule. So it's over x squared plus 2x squared. And that would be my final answer. And I kind of ran out of room here, so I'm going to do this problem down below. So g prime of x will equal the bottom, x squared minus 6, times the derivative of the top, that's a 1, minus the top, x plus 2, times the derivative of the bottom, that's a 2x, over the bottom squared. So I'm going to simplify the numerator again, and that will equal x squared minus 6, and then I'm going to distribute the negative and the 2x at the same time. So this is a negative 2x squared minus 4x over x squared minus 6 squared. So I'm going to combine like terms in the numerator. And I have an x squared subtracting 2x squared, so that is a negative x squared minus 4x minus 6. So I could factor out a negative and put it to the outside or move it down to the bottom, and it might look prettier, but it's equal to the same thing. So x squared minus 6 squared, and I've done the quotient rule. So I have two more examples to show you. H of x is actually written as the quotient of two different functions, but you don't really know what function g is, but I know it's a function of x, and I know f is a function of x squared. So this is composition of functions, and that x squared is going to be my u. So we're using the chain rule in combination with the quotient rule. So h prime of x will equal, it's the bottom function, 6f of x squared times the derivative of the top times 5g prime of x minus the top function, 5g of x, times the derivative of the bottom. That will be 6, and then the derivative of the outside function f is f prime, leave your u alone, so x squared, times the derivative of your u prime, a 2x. So bottom, derivative of the top, minus top, derivative of the bottom, all over your denominator, the bottom, squared. So 6 f of x squared squared. And then you could simplify all of this, and you can see that there's a 6 in each one of these. There's not a 5 in everything, but you could take out a 6. You could try to, just put the 5 out front, so it would be 5 f of x squared times g prime of x minus 5, and then I'd have a 2, so a 10x g of x f prime of x squared. I would still have 1 6 left here, so a 6, then the f of x squared would still be squared. So you could simplify this, but it really just depends on what you're using it for. For j of x, I wanted to show you one more with u substitution with the chain rule, and you have a u right there where the tangent is, so it's tangent of u. So j prime of x will equal the bottom, tangent of 3x, times the derivative of the top. That's a 2x plus 1, minus the top, x squared plus x minus 6, times the derivative of the bottom. The derivative of tangent is secant squared, and I'm going to leave my u alone, of 3x times my u prime. The derivative of 3x is 3. And it is all over the bottom squared, so tangent of 3x squared. Now you can see that I could do a lot with the numerator. I'm not going to do anything with the denominator, but you have done the quotient rule one more time. The last problem I wanted to address was, when do you not actually have to use the quotient rule if you have division? So let's say that we have k of x equals x squared plus x divided by x. So there are different ways to approach this, but you've got a function here, and actually I'm going to even put, no, I'm going to leave it alone. So I've got one term in the denominator, and it's easy to take a derivative of, and it's related to these other terms. So instead of doing the quotient rule, what I can actually do is just simplify the equation. This is x squared divided by x plus an x divided by x. This equals x plus 1. And then I can take the derivative of it, and I actually just get 1. So k prime of x equals 1. So I didn't need the quotient rule. Now if I do the quotient rule, I should end up with the same thing. So we're going to do that. So it's the bottom function, x, times the derivative of the top. So 2x plus 1. Minus the top function, x squared plus x, times the derivative of the bottom, 1, over the bottom squared. So I'll simplify my numerator, and I get 2x squared plus x when I distribute this x in, minus x squared minus x over x squared. That's still k prime of x. I have a 2x squared minus x squared. That leaves me with 1x squared. X minus x, those cancel out over x squared. This is my k prime of x. And you can see that that is equal to 1. So in this case, I didn't need the quotient rule, but that's because there's one term in the denominator and I could actually split it up on each term. If you have more than one term in the denominator, you're probably going to be using the quotient rule to actually take the derivative.